questions with calculations. Oh, okay. This is where a lot of people have trouble in converting units. If this takes some practice and getting used to it. We use prefixes instead of writing everything out with, 12 zeros. We use milli, and it's lowercase, to represent 1,000. I think that's comes from the Latin, a milla, something.
Millennium.
I don't remember exactly, but it represents 1,000th of a quantity, not 1,000, but 1,000th, 1/1,000. So a lot of times we'll deal, we don't deal with amperes as much as we do milliamperes and microamperes. So a milliampere is 1,000th or 0.001 amps. Or if we represent it in scientific notation, it's 1 × 10⁻³ Is everybody familiar with scientific notation?
Yes.
So all we have to do is add and subtract exponents in order to multiply and divide. A micro, is how we talk about a millionth of a quantity, or 1 × 10⁻⁶. Like a microvolt would be 0.000001 volt. So it's a lot easier to say a microvolt than to do decimal point and all those zeros. On the milli, we normally represent it with a small m, lowercase m, because we use a capital M for mega, which we'll get to on the next chart. We represent micro. Technically, we use the mu Greek symbol, but you don't always have that on your laptop or whatever, and a lowercase u is used in a lot of cases if you can't do a mu symbol. The next one is a pico, and actually I skipped one in the middle because I didn't have room on the chart. But we'll talk about it in a minute. There's a nano. The pico is a trillionth, or 1 × 10⁻12. And we use the small lowercase p to represent a pico. The one I skipped is a nano, which is 10⁻⁹. And you notice all these go up in orders of 1,000, or 10 to the third. So we get the minus 10⁻�3, 10⁻�6, 10⁻⁹, 10⁻⁴. There's one 10⁻⁻⁵, and I don't remember what it's called, but probably a femto, something like that. You won't really have, that won't be on the exam. Okay, when we go in the opposite direction for larger ones, we use a kilo, like you're familiar with in a kilometer or a kilovolt. The one thing that's different about it that you need to remember, it's a lowercase k, whereas all the others are going to be capital letters. So that one gets a little bit confusing.
Yeah, I don't know how that happened.
Yeah. So a kilohertz is a lowercase k, a capital H, and a lowercase
I think we
z.
should have kept it all lowercase.
We use mega to represent a million, okay, or 10 to the 6th. And commonly talk about megahertz. All of the amateur frequency bands are in the megahertz range. Well, virtually all of them. I guess the really low frequency stuff, which is now part of that, is below a megahertz, but HF is in the megahertz range, and VHF is the megahertz range, and part of UHF. Giga is the next one up, which is 10 to the 9th. And we talk about giga. Some people say it's giga. I don't care how you pronounce it. It represents 10 to the 9th or 1,000 megahertz. I think the next one is a tera, wouldn't be a tera, which would be 10 to the 12th. Okay, like in your computer storage, we're up into terabytes now. Very ultra high frequency would be in the terabytes, but that's in the amateur range, but you're probably not going to be doing terahertz stuff in the near future. This little chart kind of shows the comparison of all of them, where we go up from kilo to mega to giga, and we go down to milli, micro, nano, and pico. And the representations for them, what they are in scientific notation and actual in decimal. So that people have trouble with is converting from one to another, like from hertz to megahertz or megahertz to kilohertz and those kinds of things. So you'll just need to do some practice on that. Some examples are if I wanted to go from amperes to milliamperes, I know that there's 1,000 milliamperes in an ampere. So if I have 2 amperes, it's 2 times 1,000 or 2,000 milliamperes. If I wanted to go hertz to kilohertz, which should have a capital H in the middle, I think. They don't always do it that way. There's 1,000 hertz and a kilohertz. So again, it's a multiplication. So I do 700, in this case, I'm dividing 700 by 1,000 to get 0.7 kilohertz because hertz are smaller than kilohertz. And that's the main thing you need to keep straight is whether you're going from a small to a larger or larger to a smaller quantity. Depends on whether you multiply or divide, or you shift left or you shift right on the decimal point. In microvolts to volts, we know that there's 1,000,000 microvolts in a volt. Okay, so to go from 70 microvolts to volts, I'm going to divide by 1,000,000 and get 0.00007 volts. So microvolts are pretty small, but it's actually the kind of signal levels that receivers see. They're down in the microvolt range. Milliwatts to watts, okay. There's 1,000 milliwatts in a watt. So if I wanted to go a milliwatt to a watt, I divide by 1,000 and get 0.1 watt. Megahertz to kilohertz. I know there's 1,000 kilohertz in a megahertz. So if I wanted to go from 14.074 megahertz, convert it to kilohertz, I'm going to multiply that by 1,000. And it's going to give me 14,000 and some odd kilohertz. And in ohms, there's 1,000 ohms per kiloohm. So if I got 10,000 ohms and I want to know how many kiloohms that is, because normally when you would specify a part, like on a diagram, you wouldn't write out 10,000 ohms, you'd write 10K ohms. So you'd divide it by 1,000. So let's see if we can do these. How many milliamps are there in 1.5 amperes? Remember, there's 1,000 milliamperes in an ampere.
See,
See,
Did you say C?
C.
Yes, C.
Okay, Charlie. Yeah, you need to start practicing the phonetic alphabet. Well, let's see if it's Charlie. Well, by George, it's Charlie. So we multiply 1,000 milliamperes per amp times 1.5 amps and get 1,500 milliamperes. So, which is equal to 1.5 million hertz. Wait a minute.
Okay.
We have an A. Any more A's?
Yes, A.
I don't know why my VPN is trying to connect. I don't want it to do that. But it doesn't like it. All right. Which is equal to 1 kilovolt. Remember, a kilo, even though it's lowercase, is 1,000 volts.
Just keeps dancing. Yeah. See, what you said.
Sorry about that. Which is equal to 1 microvolt. I'm not going to tell you this one.
1 million of it, though.
Which is equal to 500 milliwatts. And we know a milliwatt is what?
At 1 million of a volt. Of a watt.
A what?
1,000? Yeah, 1,000.
Thousand.
1,000.
Bravo.
So I would do, yeah, the
E.
4.5.
Bravo.
Bravo. Very good. Which is equal to 3,000 milliamperes. Now, after a while, you don't have to think about these. You can just see it.
I'm gonna say
E. Delta.
Delta. What is the abbreviation for kilohertz? I mentioned before, this is a tricky one.
delta.
Delta.
Very good. What is the abbreviation for megahertz?
Delta again.
Delta.
Yeah, I need to make sure on these because my word processor tends to capitalize these at the beginning, even if you don't want them.
Disable that.
And you
I disabled mine.
have to go back and check them because if you do something and they automatically say, oh, you really meant this. Which is equal to 3.525 megahertz. Now, here's one you asked about that's not a nice round number,
Charlie.
but all you have to do is move the
Yeah.
decimal point.
Yeah, that's what I've been doing all along. Okay, that's my point.
And that's one way to remember it. Do I go left or right on the decimal point? 3 places or 6 places, what, you know. Which is equal to 28,400 kilohertz. And most of them are megahertz, one of them is in kilohertz.
Delta.
Yeah, delta.
Delta. Which is equal to 3,425 megahertz.
Charlie.
Yeah, Charlie.
Charlie.
I think the reason they put that in there, that's the cell phone frequency. And amateur also. We share that. Which is equal to 1 million picofarads. Remember picos? 10 to the minus 12.
Bravo.
Beta.
I'm gonna go down.
Bravo.
Well, we got mostly Bravos. Bravo wins.
I went by 12 zeros. And I know I had to somehow move 12 zeros, although it wasn't easy, but
Well, you only had to go 6. It was pico to
I know, yeah.
micro.
Right.
Okay. Well, this is another fun one. Only 1 or 2 questions, I think, maybe only 1. We use decibels to represent ratios. And it's a logarithmic function. This is one, well, for the question they asked, you don't really need the calculator. But for power, because we talked about power, voltage and current are the square in the power formula. So that's why if you're doing a voltage gain or a current gain, it's 20 times the log. Whereas if it's just a power gain, it's 10 times the log. And the only reason those multipliers are there is just to give it a slightly bigger number instead of dealing with things at the decimal point level all the time. So the formula for power gain is 10 times log base 10 of the ratio of the 2 powers. Okay, so if you had, if P2, let's say, represented the output power and P1 represented the input power, let's say, of an amplifier, then that ratio, let's say it was 100 watts out and 10 watts in. So we had a ratio of 10. So if I take the log of 10, which I don't remember off the top of my head, and multiply that by 10, that's going to give me the power gain in dB. And we represent that as a small d and a capital B because it represents a Alexander Graham Bell's name, Bell. So these are what we call them decibels. They're smaller than bells. They start off, AT&T back in the telegraph days start off with bells, and it was just too large a unit, so they kind of settled on decibels and a way to measure it. So the normal ones that you will be dealing with, particularly on the exam, are things like 3 dB is a ratio of 2 to 1. Minus 3 dB is a ratio of 1/2 or 1/2. 6 dB is double 3 dB, obviously, so it's a ratio of 4 to 1. And minus 6 dB is 1/4 or 1/4. So you can see where this is going. So 9 dB would be a ratio of what? 8 to 1, right? And minus 9 is going to be a ratio of 1/8. When we get to the multiples of 10 dB, okay, is a ratio of 10 to 1. Because even though I couldn't remember it at the time, the log of 10 is going to be 0.1. So 10 times 0.1 is going to give me, wait a minute. Let me back up. The ratio of log of 10 is going to be 1, and 10 times that is going to give me 10 dB. If I had a ratio of 20, I'm going to get 20 dB. If I had a ratio of I'm not. Let me back up. I'm getting messed up. Ratio of 10 is going to give me 10 dB. A ratio of 100 is going to give me 20 dB. A ratio of 1,000 is going to give me 30 dB. So they go up in those powers. That's why you can represent graphs if you do it in a dB or logarithmic scale and represent 0 to gigahertz in a very narrow graph. Whereas if you tried to do that linearly, you'd have no resolution down at the low end at all. So it's just a way that, and things show up better on plots a lot of times. You can see the stuff.
Robert, this is Smokey.
Okay,
Can I offer something?
okay,
The log of 2 is 0.3010.
that's true.
If you
We
just
round it
remember that, yeah, it just rounded off.
All right.
Don't know if that helps, but
And as far as when we actually use these, we normally will write them as, like in the case of antennas, dBi, which is a dB relative to the isotropic radiator, which is a theoretical point source antenna. It doesn't exist in the real world, so that's why it's a reference. So it's antenna gains relative to that reference antenna. Sometimes we also use a dipole antenna as a reference, and if it's referred to that, we represent it as a dBd, or a dB relative to a dipole. Sometimes you will see, like in audio and things, a dBm, which would be a dB relative to a milliwatt of power output or sound. Sometimes you have dBV or dB relative to a volt. I don't see that often, but and there's others where
My
you're doing
signal strength right now is negative 90 dBm here.
okay. Main thing to remember, it's a logarithmic scale, and any of your calculators should be able to do a log base 10 function, which is not the same as the natural log, which is usually ln, or natural log, which is not base 10. And we don't deal with those in this course, or the next one, or the next one. Okay, so which decibel value most closely represents a power increase from 5 watts to 10 watts? So the power ratio is what? 10 over 5, right?
This is 3. Yeah. 3 dB.
So ratio of 2 is 3 dB, right? So you do the out over the in. Now, if it had been a lower number, it would come out negative because you get a negative log sign. Which dB value most closely represents a power decrease from 12 watts to 3 watts. So we're gonna do out over in, which is what, 3 over 12?
Yeah, I don't have that now.
Yeah, Charlie?
Yeah. I'm
It's
gonna-
1/4, right? The ratio?
Yes,
Okay, so 10 log times 1/4. Or 10 log of 1/4 is -6, right?
96.
And if you don't believe me, there it is. Which dB value most closely represents a power increase from 20 watts to 200 watts? So 200 over 20, ratio is 10.
Okay.
Log of 10 is
A.
be right.
Okay.
Log of 10 is 1. 10 times.
I'm only saying that because the other ones don't know shit.
Well, that's the other way to do it. Look at the ones that are wrong and eliminate them. Okay, oh. So you just need to remember these relationships for the prefixes. And they're all factors of 1,000. Either going up or going down, so you're shifting the decimal point 3 places at a time, depending on which way you're going. And with a little practice, it won't be hard at all, but a lot of people have trouble with that. You need to remember the formula for dB. And this other one we didn't talk about. The difference between a dB relative to a dipole and a dBi relative to isotropic is 2.15. So a dipole has 2.15 dB more gain than the theoretical point source antenna. Manufacturers for antennas will normally use dBi because it gets them a bigger number. So they can say the gain is 2 dB higher than if it was compared to a dipole, which is essentially the simplest antenna you can do. Any questions on those?
And on marketing when you're trying to sell the antenna.
Yes. Yeah. It's always the money.
Always the one.